Hi, so we're going to talk about the removal operation in the binary search tree. So we had a insert operation to insert a piece of data. So very naturally, we want a remove data operation to remove some data if we want to. And this will be the last operation that we'll implement for binary search tree. It's actually one of the more complicated operation, if not the most complicated one. And it's in some ways similar to insert in that it changes the structure of the binary search tree, although it does this in a somewhat interesting way, a different way from insert. And well, one thing I want to say is, yeah, in this case, it's a slightly complicated code, so I'm not going to type it out on the fly. I already typed it. I'm just kind of talk through and try to explain how the code works, but I will show you when we run the code. Okay, so the overall strategy for removal is, well, we're given the data, so we have to find the data first, right? And when we find the data, we have to do it recursively as usual. And then once we find the node that contains the data we want to remove, we'll try to remove it, and we'll try removing a node can be kind of disruptive to the structure of the tree. We'll try to minimize the disruption. And so there are quite a few cases that we have to think through. Okay, so let's start with the usual pattern of these methods that we've kind of employed for a few other operations already. So the first thing is, yeah, we have a public method for removal, and we take the data as a parameter, and we have a private recursive version that we will call from the public version, and we'll give it the root. We'll always start at the root, right? And here's the private recursive version. Now, a few things to note, even for these patterns that we've already seen. One thing is, just like the private recursive version of insert, the private recursive version of remove will return a subtree, okay, with the data removed. Now, the subtree that it returns, it may be, well, when we return a subtree, we always talk about just returning the root node of the subtree. That root node, most of the time, it's probably the same root node that we start with. Okay, now there are going to be cases where the root node changes. For example, if the root node is the node that actually contains the data to be removed, so that root node would in that case be removed and be replaced by something else. So in either case, the underscore remove will return the root node of the subtree with the data removed, and therefore we will always update the root node of the subtree with the one that's returned by underscore remove. Okay, and now we can look at the kind of the simple base case for underscore remove. So the first thing is always, if the subtree is empty, then we couldn't find the data that we are removing, and we're done. Okay. The recursive case is, if the data we're trying to remove is less than the data at the root of the subtree, then we recursively go down on the left subtree. And if the data is bigger, then we recursively trying to do the removal on the right subtree. All right, so how do we actually remove the data when we find it? So let's look at a picture first. So in this case, we're going to remove 23. Okay, and 23 is pointed to by the root node of the subtree. And the thing to know about the node 23 is it has both the left and right children. Both of them are there. Okay, so in this case, how do we remove 23? So it takes several steps. The first step is we will find the minimum on the right subtree. And in this case, the minimum on the right subtree is 31. The next step is we will copy this minimum, 31, to the node that is being removed. So we're copying 31 to this node, which previously contained 23, and we're trying to remove. Now, I'll leave that to you to figure out why that's okay. But hopefully it's obvious. And then the last step is now we have 31 and 31. And remember, we don't allow duplicate data in the tree, and we're really trying to remove a node, right? So we should remove the leaf node, the minimum one that we've already copied over. So we'll remove this node that contains 31. And the fact that this is a leaf node makes it really easy to remove. And that's what we'll consider next. But before we do that, let's look at how we actually write the code for that. So here's the code. If we didn't fall into either of these cases, that means we find the root node of the subtree data is equal to the data we're trying to remove. So we're trying to remove now. And in this case, this root node has both the left and right children, like the picture we just discussed. So what we'll do is we'll find the minimum on the right subtree, and then we copy that data into the data of the root node of the subtree, which is the one we're trying to remove. And then we'll recursively remove the data that we just copied over in the right subtree. Okay, so if this is not clear to you yet, so then go back to the pictures, look at them again, and stare at this code for a little bit, and I hope that it makes sense. Okay, moving on. We just said, okay, how do we actually remove a node? So, and I said, if it's a leaf node, it's an easy case. So what makes a leaf node is that a leaf node has no child at all. So that should be fairly easy to remove. And all that we'll do is, let's say, we're trying to remove the node 5. Okay. And all that we're doing is then just set the root node to point to none. And we return this subtree back up the call stack so that its parent node, which originally pointing to this subtree, would now point to the new subtree that is empty. So that's how you remove a leaf node that has no child at all. Now, if a node has one child, that's also very easy to remove. So in this example, the the node we're trying to remove again is 5, and it has one left child that is 3. So in order to remove 5, all we have to do is, well, we'll point the root node to the child of 5, right? And then this becomes our new subtree, and we'll return the new subtree to the parent up in the call stack. And we'll have that parent will point its left subtree to this new subtree that does not have 5 anymore. And so that's how we'll remove a node that either has just one child or no child at all. Okay, and here's the code that does it. And this is the last case here. And basically, this else really means, remember, this one is in the case where there's both a left child and a right child. So if that's not true, that means we either have only one child or no child at all. So in that case, if there's a left child, then we want the subroot to become that left child, right? Just like this picture. If there's a left child, then the subroot would become the left child. And otherwise, the subroot would just becomes the right child. The right child might be, just the only child there, or the right child may be a none. So either case, it doesn't matter. Now, what happens in either of these cases is that we are physically really shrinking the subtree by one node, right? So the size then has to be decremented by 1. And in this case, as we said, the subroot has changed, so we have to return the subroot. Now, in the all these previous cases, well, actually, in particular, this previous case, the subroot did not change, and we still return it. So either of these cases will return the subroot tree. Sorry, I will return the root of the subtree. All right. Again, if this doesn't immediately make sense, go back to the pictures, stare at the code, think through all the cases, and hopefully it will make sense. So now that we have implemented remove, we should really test it. So I've already written a test case, and as a matter of fact, the BST that I constructed should look exactly like the BST that I am using as an example here. So, and let me just quickly go over. I mean, it's what you expect. That I constructed a BST. I have a list of data. I insert the data from this list. I remove 23 from the list of data as well as my BST. And then I create a list from my BST, and I make sure that the list from my BST is the same as the list of the original data with the 23 removed, of course, and I make sure the number of data in both list and the BST are the same. So if I run this, and it works great, and I also printed out the BST just to make sure that it looked like the picture in my slides, and you can kind of verify it. If you again look at it sideways, the 23 is at top. After the 23 is removed, now the number 31 is at the root of the tree. Okay. Now, so enough talking, and I think, as I said before, it's important that you kind of step through the code either by hand, or you can step through the test code in the debugger to really understand how the removal works in a BST. And if you want, obviously, if you want more kind of exercise to ensure that you understand everything, then you can try to remove other numbers as well. Okay, so that removal was just removing a single number, although I think it actually covered quite a few cases already. Now, for good or ideally complete test coverage of remove, we can carefully construct a BST and then pick not just one data, not just 120, not a single number, but we probably should pick a few numbers just to make sure, all conditionals, all branches inside the remove are all tested. So that would be a handcrafted complete test coverage of the removal method. I'm going to show you a different strategy that is optional, but I think it's good to know. So what I'm going to do is I'm actually going to generate a random large binary search trees, and then we start randomly removing its data one by one until they're all gone. And then at every step of the way, I would verify the BST is what we expect. So the hope in this strategy is that when the BST is large enough and random enough, then we will, cover all the cases that remove would run into. Now, the flip side, the disadvantage or the peril of doing this is the test itself is actually pretty complicated, so it can be buggy. And when a test is buggy, it's even harder to debug than your normal code. And also, you may or may not know this, it's actually very hard to have something that is truly random. And it actually took me quite a few tries to get this thing right, and I think I got it right now, but it does take a lot of practice to get this right. So I already have the code here, and I'm gonna just kind of quickly explain to you what I'm doing here. So the first thing you notice is, I construct a BST. Now I do a random seed, and I give it a fixed C. What that does is, even though it does generate random numbers, it will generate the same sequence of random numbers each time. And the reason for that is it's important to have reproducible tests so that if there is a bug, we can do the same test again, and then we debug it. Right? If every time it's completely random, it's completely different, then if there's a bug, sometimes some tests will succeed, other times the test will fail, and that's really, really hard to debug. So anyway, that's why I give it a fixed random C. And what I'm doing here is I'm using the random sample. So I'm going to generate, here is 1,000 numbers, and the random sample is going to pick 100 numbers from the 1,000 numbers, and it's going to insert into the binary search tree. And then the next thing I'll do is for the data to remove, I don't want to just remove from the beginning of the list of data, because that's the order in which the data is inserted into the BST. So, and that might have some weird effect if I do two things in exactly the same order, the insertion and removal. So I want to remove data randomly. So I'll again create a random sample from the data that I already it's not a sample. I'm picking everything from the data I already inserted into the BST, but in a different kind of random order. Okay, And now I'm going to go through all the data that I want to remove. I'm going to remove it from the list of data, and I'm going to remove it from my BST. And then again, same strategy that you already see, that I'm going to construct a list from the BST. I'm going to make sure that list is the same as the sorted data. And then I really should have a check for the size here as well. But finally, I want to make sure that if I already remove a piece of data and then I remove it again, it would raise a not found error. So that's that. Okay, so good. The actual code actually does also check the size of the list and the size of the BST as well. So all right, so let me run this and I'll show you what happens. So here is the original tree with 100 or 99, I guess 99 numbers. It's a pretty big tree. And then we start removing kind of just random numbers, and then I print out the tree again, just print it out. So that's how I kind of verify that my test does work, or my randomly generated tree does work. And then with these couple asserts, and that it seemed that this test does pass, and kind of work on a tree with 100 or nodes. And when you get to the very end of the test, um, we get down to size of 1 and finally size 0, and the tree is completely empty. So this is an example of a fairly robust test that uses a large randomly generated set of data.